Hello everyone and welcome back to Thermo Shorts. We've been looking at open systems and particularly how to do the first law of thermodynamics on these open systems. So we have an equation for the open system first law, but we have to remember that even using the metric system, units for kinetic and potential energy can be difficult. This is even more true when we're talking about imperial units, because here not only are the units difficult, but just to get the right quantities, we have to divide these same two terms by GC. So we're going to talk about doing the first law on turbines and pumps today. So I showed last class that after we make a series of assumptions, we'll typically get that the power either generated or consumed by these components is the mass flow rate times the enthalpy coming into the system minus the enthalpy going out of the system. Now, one way to kind of remember this is that the Disney characters, the seven dwarves, are some of the hardest working people in all of show business. And the song they sing is Hi Ho. So if I'm trying to calculate power, I get m dot times h in minus h out, at least if I can remember all of the right assumptions. The example we're going to do today deals with steady state of a turbine. Now, you might remember this turbine from the same example that we did for mass flow rates. This is all the same information. So we've already done part of this problem to find the velocity at state 2 and the velocity at state 3. But in this case, we're going to try to find the work generated by this turbine. We've got some assumptions listed at the bottom of the slide. So we'll start with our first law. I always want to start with the base level of the first law and then explicitly make my assumptions as I cross terms out. Now in this case, we know the velocities at state 2 and state 3. I'll make an assumption about the velocity at state 1. So we can include the kinetic energy terms here, and then I'll show you that they end up not really changing the power that we generate from this turbine. After I do this, I get this equation. Now remember, my turbine has one inlet and two outlets. In this case, I'm trying to find the power. I don't know any of the specific enthalpies yet because I didn't fix the states. I know the velocities at state 2 and state 3, but not at state 1. The first thing that I'm going to do is make an assumption about the kinetic energy coming into the system. Here, I've assumed that it's 10.7 meters per second, but we'll see whether or not that's a reasonable assumption, and would it matter if I picked a velocity of 17 meters per second or even 20 meters per second. So after I make this assumption, I'll go ahead and find all of my specific enthalpies. To do this, I have to fix all of my states, but I trust that you know how to do this now, so I'll just give you the values for H. Now, we can put all of these things into our expression from the first law for the power generated by this turbine. I'm going to evaluate each one of these terms individually, where each term is related to a specific state point in our problem. So first, I take state 1. Now remember here, I didn't actually know the velocity, I just assumed a value. But when I put this in and I get my units right, I see that the enthalpy is very large compared to the kinetic energy at this state. In fact, the kinetic energy, when I put it back into kilojoules per second, or kilowatts, is very small compared to the enthalpy. So maybe my velocity assumption was wrong here, but I'm not sure it really matters because the kinetic energy term here is so small. So now let's do the same thing for the second state. And again, we see that the kinetic energy term, even though the velocity here is larger, the kinetic energy term is still very small compared to my enthalpy term. I'll evaluate this again at state 3, where we find the same thing, that this kinetic energy term, once we get the units right, is very, very small. So if I calculate the power when I'm including the kinetic energy, I get 9.75 megawatts produced by this particular turbine. What would happen if I did the same analysis and I neglected the change in the kinetic energy as I'm looking at all three of these different states? It turns out that my answer doesn't really change. So this is also 9.75 megawatts. The difference between this solution and the solution where we included kinetic energy is very small. So there's two take-home messages here. First, oftentimes the enthalpy change dominates the kinetic energy. But the second thing here is if we do include the kinetic energy terms, we need to make sure we're getting the units right. Otherwise, we might think that the value of these terms is much higher than it really is. Thanks for joining me on Thermal Shorts. I'll see you next time.